Hello, Pre-Calc students. This is Mr. Beck. Today we're going to be talking about Chapter 4. We're going to introduce our next series of functions. But before we do that, I'd like to go back and say where we've been. In Chapter 1, we talked about a bunch of individual skills. One of those skills that we talked about was lines and finding the equations of lines, working with lines, etc., etc. From there, we went on into Chapter 2. Chapter 2, we introduced domain, range, topics that we've discussed before mathematically, but we went a little bit further with it, function notation. We talked about functions increasing and decreasing, and they increase to decrease at a relative maximum, and then they decrease to increase at a relative minimum. Then we went into 2.4, which we discussed our library functions, our parent functions. Some of those parent functions include the absolute value function, the square root function, the cube root function, the square function, the cube function, just the identity function, which is y equals x, and then the reciprocal function, which is y equals 1 over x. So we introduced a lot of those different functions, and we did the greatest integer. But one of the big things that we did from there was we took it and we dilated, reflected, and translated those power functions. Sorry, those parent functions. There we go. Then we went into Chapter 3, and then we went into more detailed explanation, working with lines. We worked with them on a level that was involving business concepts. Then we did quadratic functions, which have a parabola shape. And with those functions, we went into more detail with the business, but we talked about different aspects, qualities of parabola, the vertex, where that is, and how the vertex is either a relative maximum or a relative minimum. And so now, what are we doing in 4.1? We're going to begin by discussing more functions. And the first type of function that we're going to be discussing is the power function. Now, a power function is a function that has the form a times x to the nth power, where n is an integer. So n is an integer. With a power function, the idea of the power function is we want to see what happens if we just have x to various powers. So we worked with a couple of those already, primarily this red one right here that you see on the screen. This red one is the line y equals x, followed by the second one that we have already seen. So that's the identity function. This is going to be the square function. So y equals x squared. While I'm over here, let me go ahead and say what is the next one on this graph. This is y equals x to the 4th power. And then on this one, we had y equals x cubed power. So we have different powers, and with those different powers come a different shape of the graph. So pretty much every parent function has a distinct shape to that graph. And this one, y equals x to the 5th. Occurs to me, I probably should call those f of x, but we get the idea. How about x to the 6th? Today is one of those days, unfortunately. So y equals x to the 6th. So all these different parent functions have different shapes. Now, there are similar characteristics that we start seeing as we look at all these different parent functions. And we say, okay, is there anything that we can quantify about what happens to all parent functions of power functions? So as I look at this one, we're going to focus on these all kind of have the same shape. Now, parabola, so this y equals x squared, hits the x-axis once where y equals x to the 4th, a little wider, y equals x to the 6th, a little wider, but we see that they all have generally the same shape. So that's where we quantify that every even power function, so when n is an even number, every even power function, we have symmetry to the y-axis. And that's why we call it even function. Domain is all reals. The range is from 0 to infinity. That's before we do any dilations, or sorry, before we do any translations. The domain or range is going to be from 0 to infinity. Key points that are on here: -1, 1, 0, 0, and 1, 1. So every even power function will go through those 3 points. Over here, if we have an odd exponent, we have, not surprisingly, odd functions. And those odd functions do have origin symmetry. So they have symmetry around the origin, and they all go through the point -1, 0, 0, and 1, 1, with a domain range of all real numbers. So those similarities are very, very key as we look at it. And with both even and odd power functions, what ends up happening is base gets wider as n gets larger. Now, the reason for this, we can look over here and we can kind of see it a little bit better. If we take 0.5 to the first power, it's 0.5. 0.5 to the third power is 0.125, which is why we have much smaller numbers. 0.5 to the fifth power is a number I can't think of off the top of my head, so I'm not even going to try, but it's a much smaller number. It's like 0.01 something. I should know this doesn't matter. Anyway, but those decimals, as they get smaller and smaller, or as they get raised to bigger powers, they get smaller and smaller, and so they start hugging the x-axis a little bit more. And then once they get past 1 and -1, then what ends up occurring is those grow faster. So 1.1 to the first is 1.1, or 1.1 to the third is 1 point something. Again, I don't know off the top of my head. But they grow faster and faster. I know 1.1 squared is 1.21. But anyway, as we look at these power functions, the way that we're going to first graph them is by graphing them just like we did all the other parent functions we worked with. So as we look at f of x equals 6x cubed, one of the things that we're going to notice is this is one of the parent functions that we already know, but we're going to view it more as a power function this time. So the power function would normally go through the 3 points, -1, -1, 0, 0, and 1, 1. This dilation of 6 causes us to make those vertical dilations of 6. And then from there, we can sketch the graph. And one of the big things I want to point out is we do have this crossing at a horizontal tangent, so in a horizontal manner. So make sure that you draw that in. Now, as we look at our next one, this even power function, one of the things, this is one that we have not done yet. So this is x to the fourth. X to the fourth typically has these 3 points, 0, 0, -1, 1, and 1, 1. But in their dilation of 5 with their reflection, basically our y values get multiplied by -5. So 1 times -5 brings that point here. 1 times -5 brings this point over here. And 0 times -5 actually keeps that point where it is. And so we have the graph going this way. One of the extensions we could do with this is say, okay, what's our domain now? Our domain doesn't change because every polynomial, which power functions are part of the polynomials, every polynomial has a domain of all real numbers. The range is going to be from -infinity to 0. As we look at our next graph, we have a couple different things going on. First thing going on is we do have this reflection over the x-axis. That reflection, and this was odd, so this reflection started with those 2 points. However, over the x-axis became these 2 points. And now we have this shift to the right 4 and up 1. So this 0, 0, this vertex, if you will, it's not really a vertex, but this vertex style point is going to go right 4, up 1, moves there, and then each of these 2 points will go there as well. For this even power function, we don't have any reflections, but we do have a dilation. So these 3 points get dilated. So this one has a y value of 1 multiplied by 3, y value of 1 multiplied by 3, and then all of those get shifted down. Now, I did kind of walk through that in the way that we've typically done all of our dilations, reflections, and transformations. Let's start looking at kind of a faster approach. That vertex point does get shifted down, and with that vertex point shifted down, we know that this opens up, and that dilation of 1 now becomes a dilation of 3. So if we look at it that way, it might be a little bit easier way for us to graph these. So as we get into our 5th degree, this is yet another odd power function. So I start looking at this going, okay, my vertex point, not really vertex, but my vertex point is -1, -2 becomes here. The dilation is 4, and it's a +4, not -4. So this point here got dilated by 4. So instead of being 1 space away, it's 4 spaces away. Instead of this one being 1 space away, it's 4 spaces away vertically. So you can graph it that way. If we apply that same kind of logic here, we're going to start off with our vertex point of 2, 4. 2, 4 is our vertex point here. Our dilation is 3, but it opens down. So that dilation open down should have just been 1 there, but it's now going to be 3 away because of the coefficient of 3. So that's how power functions work. And when it comes to power functions, fairly straightforward, and it's a good refresher on how to work with dilations, reflections, and translations just with new styles of functions. And what happens if we don't have anything that is a strict power function? Most likely, we're not going to have it because we don't usually just have one variable there to a power. We have multiple variables like x cubed plus x squared plus x plus 1. So we have a sum of a bunch of power functions. So to work with a bunch of power functions, I kind of proposed a chart here where I said, okay, what are all these different functions? We can see that we start off with f of x equals a, then ax plus b, ax squared plus bx plus c. Basically, we are getting 1 degree higher every single time. We can see that we start off with degree of 0, degree of 1, degree of 2, degree of 3, degree of 4. I'm going to go ahead and erase those just so it doesn't look quite so messy. So we raise the degree each time. Now, a degree of 0 is called a constant function, and we know it's y equals whatever that a value happens to be. A degree of 1 causes us to have a linear function, and all of these are leading coefficients. So a linear function with a positive leading coefficient, aka slope, is going to increase over the entire domain. A positive quadratic opens up, concave up is what we call it. Positive third degree is going to start at the negative and then go to positive. And a positive fourth degree starts at positive and has a W shape. Now what's happening each time is we're adding another what we called turning point. So in algebra 2, we refer to those as turning points. How many times does this function turn? And as we kind of think through what we've done in pre-calculus, we stopped calling those turning points and we called those relative extrema. Kind of hard to see that because I scratched it out, but these are relative extrema. So a second degree has at most 1 relative extrema. A third degree has at most 2 relative extrema. A third degree has at most 3 relative extrema. And there's a connection to calculus here, which is going to be really, really fun for you guys to see next year, and I'll leave that for next year. But we have at most 1 less than the degree for how many relative extrema we have. Just because we can have a relative extrema doesn't mean we do. In fact, if you look at the cube power function, which has this shape, we don't have 2 relative extrema. In fact, we don't have any relative extrema, and that's okay, because that's why we said at most. But if you notice, these sort of have the same general shape, so we can use that general shape for benefit. And the biggest benefit we have is, what is the end behavior? Now, in algebra 2, you guys looked at this and said, okay, this side goes down, this side goes up. Okay, that was a great introduction. I love that as an introduction. Now let's start looking at it a little bit more mathematically. What does this mean? The fact that it goes down, great, but we're going to say as x goes to negative infinity, what does the y value do? It goes down. So this says the limit as x goes to negative infinity, the y value also goes to negative infinity. And as x goes to positive infinity, what does the y value do? Well, as x goes to positive infinity, the y value also goes to positive infinity, which, if you see, is actually the same end behavior for every single odd function. I do have the 5th degree polynomial that I drew in here as well, which also has the same end behavior. Now, odd polynomial functions, or degree that's odd for the polynomial functions, will have that same end behavior. And one of the things I'm going to expect you to do is be able to use the limit notation properly. One of the purposes of the course is to really help you prepare for calculus, hence pre-calculus. And in calculus, we use this limit notation quite a bit. This is our first real use of the limit that's going to have true meaning for you. And I want you to make sure you know what's going on with that. Now, what happens if it's an even degree? So if it's an even degree, then if you remember in algebra 2, we said up, up. So as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to positive infinity. So we read that as the limit as x approaches infinity of our function f of x is positive infinity. And positive infinity, positive infinity. Now what happens if you have a negative leading coefficient? Well, all of these reflect over the x-axis. So through that reflection, we see that everything is pretty much opposite of each other. We go from positive infinity to, so As x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. So on the left side, we go to negative infinity. On the right side, we go to negative infinity. On the left side, we go to infinity. On the right side, we go to negative infinity. On the left side and the right side, we both go to negative infinity. So these are going to be completely opposite of what the positive leading coefficients were. We could use that to our benefit. Now, guidelines for sketching polynomial function. One of the things that I'm going to say is what is in the book is kind of a very, very detailed approach to sketching polynomial functions. Feel free to look at those and do those as needed. I'm trying to come up with a good way of being able to say, okay, what's going to simplify our process, help us understand what to do, but at the same time not skip over some of the beautiful details that are in the textbook. So this is my general guidelines. Find intercepts. Hey, intercepts have been very, very important since we've done chapter 1. We've identified the intercepts of everything. Why stop here for our polynomial functions? Now, what's sort of new about that is intercepts can have what's called a multiplicity. The multiplicity is how many times that 0 occurs. So we're introducing this terminology of multiplicity. And the number of times a 0 occurs is going to be beneficial for us because it's going to create certain aspects that are going to be similar to each other, and we'll explore those. Then this whole recreating the power function around the 0, I will explain as I go through this. This is not like absolutely required, but I have a lot of students who say, what is that graph supposed to look like near the x-axis? And that's what I'm going to go through. We do want to identify the overall degree, so we need to know the degree, fit our general sketch, and those general sketches is what I did up here. And then we're going to check the accuracy of the graph. And when checking the accuracy of the graph, typically this is where the y-intercept is going to come into play. Basically, is my graph where what we consider is supposed to be. So let's look at the first problem. So the first problem that we do is we will say, what are the zeros? Basically, what are x-intercepts? So we identify where does this factor equal 0, where does this factor equal 0, where does this factor equal 0, which is -4, 1, and 3. That's the benefit of what we call intercept form. Just as a quick side note, all these power functions were more of like the vertex form of a quadratic, where what we're working with here is more of the intercept form of a quadratic, but they're not quadratics. This is now a cubic. So we're going to use that to find the zeros. And once we find the zeros, also, why not throw in the y-intercept, because it's just natural to find all of our intercepts together. Now, multiplicity, how many times does each 0 occur? And what we're going to look at is what's the exponent of each one of these. We don't see an exponent, which means that exponent really is 1. If we add all 3 of those together, that's how we get our overall degree of 3. Now, is this a 3 with a positive or a negative leading coefficient? Since that's positive 2, it's a positive leading coefficient, which means it has this shape, and we can fit in on the left side, it's negative infinity, and on the right side, it's infinity. So as we go to do our sketch, we'll say we're going to start at negative infinity, kind of like what that does. Negative infinity, we're going to go through -4, and then I believe that in algebra 2, you learn that, hey, this is going to go straight through, and straight through. And that's okay. I'll refer to that a little bit more later. And then this is where the check comes in. What was my y-intercept supposed to be? My y-intercept was supposed to be positive 24. And so since that is a positive value, this makes sense for me. Once we get into some of the more detailed polynomial functions, this is kind of one of my ways of checking, just to say, did my y-intercept lie where it was supposed to? Now, there is the overall question of how do we know that point or the relative maximum is right here? We don't. The way we're going to learn how to do that algebraically is through calculus. Since we're not in calculus yet, we're not going to worry just as much exactly where that's going to be. What we're going to worry about instead is, can you make that roughly halfway in between your x-intercepts? Is that ideal? No. Is that accurate every so often? Yeah, a lot of times it is, but you're not guaranteed. And because you're not guaranteed, right now we don't have enough information for us to be able to determine that very well. So let's continue on. So first thing that I do when I look at this problem, I'm going to go ahead and change colors. So first thing I say is x-intercept of -5, x-intercept of 3, x-intercept of -1, x-intercept of 1. And from those x-intercepts, once I like to list those in numerical order, All of these have a multiplicity of 1 because they occur once. Because of that, they go through in what's called a linear way. So it is a negative leading coefficient, which causes us to have a negative fourth degree, putting all that information together. And a negative fourth degree goes from negative infinity, goes through, like I said, linearly. I said that intentionally because I'm going to use that information. Comes down, goes through this linearly. Going to continue on going through linearly and going through linearly to negative infinity at the very end. And now is the time for the check. Y-intercept is 0, comma, negative 45. Since that crosses the y-axis below in a negative number, I would say that I'm on the right track with this problem. Again, that's not a guaranteed check, but I can't tell you how many times I've caught myself being on the wrong side of the axis for this reason. So moving on to some level 2 problems. This is where we're going to introduce a multiplicity other than 1. So once again, x-intercept of negative 1, x-intercept of 2, x-intercept of 4. Now, this 2 has a multiplicity of 2, which we can see right there. The other two have a multiplicity of 1. And so, with that in mind, I do see this as a negative. Add up all of those multiplicities and we get 4. So this is a negative fourth degree. You've already seen one of those, but it has this shape. So we start at negative infinity, go to negative infinity. And now, as I explore this a little bit more, what this means is we are going to go through our first one in a linear way, the second one in a quadratic way. That quadratic is due to the multiplicity of 2. And then the third one we're going to go through in a linear way. Now, this is what I am going to explore for just a little bit more. So this is not something that's going to be assessed, but it goes back to that question of how do I know what shape it is going through? So what I am going to do is I'm going to toggle between this and Desmos. So I have Desmos opened up and you can see I have this graph that I had just sketched on the other, or like in my page. So I said this goes through negative 1 in a linear way, and we can see that. The question is, how linearly? And so the answer to that is, if you look at this, I am going to, in green, say, what is the line that kind of resembles what's going on there? Now to find the line, we want to say what is happening near negative 1. So what is happening near x equals negative 1? And to figure that out, this is where the limit comes in handy. Now, I am going to stress right from the beginning, the limit as it approaches negative 1 of our function f of x means if we plug in negative 1, we will get negative 2 times 0 times negative 3 squared times negative 5. Now, what is that? 0. And we know it's 0. We've known it's 0 for a long time. That value is 0. However, to establish what is the line, so what is the line near x equals negative 1, what we're going to do is we are going to plug in negative 1 everywhere except for the factor that gives us negative 1. So negative 3 squared, and I'm going to say f of x equals, and then negative 5. And if I multiply those together, I will have 9 times negative 5, which is negative 45 times negative 2, which is 90. So near x equals negative 1, I have the line 90 times x plus 1. And if you notice on Desmos, I do have that 90 times x plus 1. And you can see how that line actually represents what's going on there very, very well. Now, even more specifically, this is the equation of the tangent line, which is kind of a cool thing. So we talked about tangent lines in previous chapters, 2.1 specifically, and 2.3. And this is where pre-calculus is setting to, hey, can we find these tangent lines very, very well? So what about this one? What about this quadratic? Well, if we go back to the function, and I will do this in a different color so it's not quite as bad. So near x equals 2, I want to know what is the parabola, or how about what's the quadratic? Let's do it that way. What's the quadratic near x equals 2? Well, we're going to do the same thing. We're going to then say f of x equals negative 2 times 3 times x minus 2 squared. Remember, we know that it's 0, but near it, we can use this limit idea and say 2 minus 4 is negative 2. Multiply those together, and I get positive 12 times x minus 2 squared. The fact that it's positive means it's parabola opening up. More specifically, if we look at that, we can see that, okay, there we go. We can see this quadratic really models the function very, very well, and it models it throughout a pretty large interval. So these are very closely connected to each other. We could do the same thing with the last one, and I did, and I get this line with the slope of negative 40 and times 4. So really, these three power functions are what are being modeled near the x-axis, which if we go back and kind of analyze our function that way, we can say what is really happening here. We have the intersection of three distinct power functions, or the multiplication of three distinct power functions. So those power functions are going to have their value, and they're going to have their weight added near their zeros. And so the power functions happen near their zeros in that way. And then it's kind of like, okay, well, this is going to be the interaction of how all the numbers in between work. This will be the interaction of how all those numbers work. So near the zeros, they all have their distinct pool, PULL pool. So kind of like a neat way to explore every single one of these if we wanted to. I'm not going to, but I wanted to talk about it and stress this is what's going on. Because students always ask, well, how do I know what shape it's supposed to be? This is our way of doing it. And our book kind of walks through a process like this also. It's a little bit more convoluted, but at the same time, it's a neat idea. So with our next one, once again, plot my zeros of 2, negative 1, 1, and 2 has a multiplicity of 2. Negative 1 has a multiplicity of 2 also, and 1 has a multiplicity of 1. Y-intercept, plug in 0, we're going to get negative 12. Now we do have a degree of 5. Once again, all of those added together give us a degree of 5. And this is a positive fifth degree. Positive fifth degrees will kind of look like this. If they are a pointed function, which means we go from negative infinity to positive infinity. And as we sketch, because of the multiplicity of 2, we interact with the 0 in a quadratic way. We interact in a linear way, interact in the quadratic way. And we get our graph. For this level 3 problem, suddenly we start throwing more and more and higher degrees at you. So once again, our 3 zeros are right here. Multiplicity of 3 for the first 0, multiplicity of 2 for the second 0, multiplicity of 1 for the third 0. Add them all together and we get 6. Plug in 0, we get our y-intercept of 0, negative 2. This is a positive 6th degree. A positive 6th degree has that shape. So we go from infinity to infinity. So infinity through negative 2 in a cubic way. And we hit 2 in a quadratic way and go through 4 in a linear way. For this one, even more, we now have a 2 plus 2 plus 3. So we now have a 7th degree polynomial function. That 7th degree polynomial function just occurred to me that I never found the y-intercept. Y-intercept looks like it's supposed to be negative. Let's check. Negative 1/9 times 9 when I plug in 0. That gives me negative 1 times 16 gives me negative 16 times 1, which gives me negative 16 also. So that should be negative 16 as the y-intercept. But anyway, going back through, I do have 2 plus 2 plus 3. Those are our 3 multiplicities. They could correspond to each 0. And now, since this is a negative 7th degree, up through 6 potential terms, and then to negative infinity at the end. So we start up, and this is a quadratic. This is a cubic power function there. And then this is a quadratic power function there. Hold on just one second. All right, with our next series of problems, what we're going to do is our goal is to find the equation of the polynomial function that fits this situation. So as we're looking at this, one of the first things that we're going to do is we're going to identify what are the zeros. We're kind of working in a reverse direction from what we did before. So we identify what are all of our zeros, and -4 is a zero, and the fact that it bounces off the x-axis means that we have more of a quadratic form. The fact that this goes through the x-axis means that it goes through in a linear way. This goes through again in a linear way, so that multiplicity is 1 as well. And so now that we have this set up in intercept form, just like what we had when it comes to lines, or sorry, with quadratics, what we do now is we say, okay, we have our general equation, but we are going to use the additional point that they give us. That additional point is the y-intercept. So when we plug in 12 for y and 0 for all the different x's, we will set this up so we can then solve for a. And in this case, we will get a equals 1/4. And so with our next one, once again, this is more of a cubic function. So x plus 3 is our factor that gives us that 0, and it goes through in a cubic way. X minus 2 is going to be our factor, and it goes through in a quadratic way, or it meets it in a quadratic way. And then we are going to use 0, -432, in order for us to be able to figure out what our a value is. Once again, plug in -432 for y, plug in 0 for x, and solve for a. On this one, this is x plus 2 to the second power because it's a quadratic, where this one, x minus 3, this one definitely is not quadratic. And as I look at this and I compare kind of like just how wide these parabolas or this bouncing off the x-axis, if you will, is, that I do feel like that's not necessarily a 4th degree, and I made it into a 6th degree. This is one of those situations where when it comes to if you did this as a 4th degree, I definitely would not count you wrong, and I wouldn't count you wrong because this is something that's just you don't fully know. So whether you do it as a 4th or a 6th degree, I would accept both of those answers. So in this case, if I do it as a 6th degree, once again, plug in 0 and 9, we end up getting a is -1 over 324. Now, in 4.1, we talk about 4.1 as quadratic or polynomial equations. What we're going to do with 4.4 is really just the inequality aspect. And if you notice, I did, in essence, a copy-paste from what we do with quadratic, and doing this as polynomial, because really they have the same kind of mentality. So what we do numerically, and I could show you this, let me kind of remove this. Let me show you this. If I know where this inequality equals 0, which would be at the intercepts or the zeros, then I test values. So if I plug in a number like -6, I will get 3 times a negative times a negative times a negative. 3 negatives multiplied together give me a negative. If I plug in 0, I will get negative times a positive times a negative. 2 negatives together give me a positive. You keep going through this. If I plug in a 3, I will get a positive, positive, negative, which results in a negative. If I plug in a 10, I get positive, 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 which is a positive. And now at this point, that's when I evaluate where is this greater than or equal to 0. So where this is greater than or equal to 0 is going to be from it equals 0 at all 3 of those points, and it's greater than everywhere in between. So now, if we look at this in more of a graphical form, what we're doing is we're looking at this as a negative 3rd degree, and it goes through all of those zeros in a negative 3rd degree manner. And when that happens, then we want to know where this is less than 0. This is going to be less than 0 in between -9 and 7, and then from 14 on. So as we get more and more complicated, then we can continue in this exact same manner. So if you plug in all the different numbers, you could do it either numerically or graphically, and we get this result. Same thing here. Notice I do have exceptions. What happens if it's just less than versus less than or equal to? How does that change the problem? So I see this as a -17th degree. I'm sorry, 18th degree. So negative is going to do something like this. It's going to cross through, and it crosses through very, very wide. And then it's going to go through Actually, this one crosses through straight, this one goes through wide. So however you approach it, either numerically or graphically, is up to you. With these last two problems, just a little bit higher level, that's where the level 3 comes in. How do you start it? Factor out the x, factor your quadratic, and solve in the exact same manner. And in this one, this is the square root. This is kind of our tie back to chapter 2 when it came to domain. What's underneath the square root has to be 0 or positive. And so we set that up as this inequality and then solve it the exact same way. So hopefully you enjoyed this, and I look forward to working with you next time.